welcome back. So, this is the second part in my chemical bonding series, which is the chapter 4 series. I will upload a third part after this, that will be the final, and then I will also add in a worksheet. There will be timestamps as usual in the description of this video, and we're going to start from where we left off. So, we finished with the dot and cross diagrams and coordinate bonding. Now we're going to move on to orbitals or orbital overlaps. Basically, we're going to discuss two types of bonds that are formed within covalent compounds. These bonds are not that prevalent in ionic bonding. So we're just going to focus on these two types of bonds in terms of covalent bonding so that it's much easier to understand. Alright, so the first bond we have is called a sigma bond. So a sigma bond is formed by the direct overlap of p orbitals. We know carbon is atomic number 6. So if I have to, let's say, draw the box electronic configuration of carbon, obviously we have the 1s, which has 2 electrons, so we have the 1s2. Then we have the 2s2, which also has 2 electrons, and then we have the 2p2 and a p orbit. This would have 3 different orbitals. Oh my bad, I'm so sorry for that. This is how we arrange our 2 electrons in that p shell. What we have in a sigma bond are the 2p orbitals of 2 carbon atoms. This is an example I've taken. We have 2 different carbon atoms here, a blue one, a red one. This black dot is the nucleus of this carbon atom, and this is the nucleus of this carbon atom. These 2p orbitals fuse together to form what we call a molecular orbital. Molecular orbital is basically an orbital formed from these 2 orbitals in a molecule, because covalent compounds are essentially referred to as molecules, which is why this is a molecular orbital. And within this orbital are where the electrons that are shared in this bond found. So sigma bonds can also be between, let's say, if we have a carbon hydrogen bond, hydrogen only has 1 electron, which is in its 1s shell. So the 1s would combine with the p orbital of the carbon atom, and then this would give us an sp molecular orbital. So it would look something similar to that one. It would just have a very tiny lobe here, and then this is where the electrons would be found within the sigma bond. So that this would be called an sp molecular orbital for the CH bond. I'm sorry for that handwriting. That's basically what a sigma bond is. It's a single bond. Pi bonds, now pi bonds build upon sigma bonds. That's actually a wrong thing to say, but the way I want to explain it is that a pi bond can only exist when there's a sigma bond. You cannot have a pi bond without one. So we have one of these 2 bonds would be a sigma bond and the other one would be a pi bond, because pi bonds form they allow the molecule to form double bonds, essentially. So more than one bond. It could either be a double bond or a triple bond, but that's what pi bonds are for. So pi bonds are formed from the sideways overlap of adjacent p orbitals above and below the sigma bond. See, that's why it's necessary, because you need the sigma bond first so that the pi bond can form. So over here, the sigma bond is already present, so I'm not going to draw that. I have drawn that later on so that you can see what it looks like when both those bonds are present. Essentially, this is two pi orbitals within the same molecule. Both of these are within these two carbon atoms. So we have these two um, p orbitals, which are like upright, and then they sort of collide this way, side by side. This is called a head-on collision because they're both colliding directly with each other, as in facing each other. These lobes, they face each other directly, so it's called a head-on collision. This is a sideways collision, so it's a side overlap, and that's a head-on overlap. So in the side-on overlap, it forms something like this. And basically, these two sort of bigger lobes would be present above and below the sigma bond, which I will show you guys later on. But this is the principle of how pi bonding takes place. It's a sideways overlap or collision of p orbitals in these two adjacent um, carbon atoms. The carbon atom is an example. This can also occur in different atoms, but for simplicity, the syllabus requires us to use carbon as our main example. So you would not be asked anything complicated at this point. Alright, moving on. I'm sorry if I'm a bit fast paced. Sigma bonds and pi bonds in molecules. Okay, so this is just me giving you guys examples based on what the syllabus says we should do. So over here we have an H2 molecule, and we're supposed to show the bonding in that molecule. H2 is essentially just hydrogen bonded to itself. It's a diatomic molecule. So hydrogen only has one electron, hence the 1s orbital of both atoms would bond together, and they would give us this weird oval-like shape in which the bond is found. So that's a molecular sigma orbital. I'm so sorry. Molecular sigma orbital in a sigma bond. It's a sigma orbital because it's a single bond. It's a single orbital, kinda. And it's the most simplest orbital you can have because they're both s orbitals that you combine or fuse, and in a sigma bond, which we've already seen here. Alright, the next example is ethane. Now there's ethane and then there's ethene. Ethane C2H6. This is what it looks like. So the two bonds we're going to look at within ethane are the CH bond and the CC bond. The CC bond, you already know what it is. It's the CH bond that is sort of the sp orbital. An sp orbital is essentially one s orbital and one p orbital. Now, like you see, the p subshell often has three boxes. When you're doing the box configuration, it has three boxes. Each of these boxes represents a p orbital. Each of them. These p orbitals, like when we were when we were drawing these p orbitals, we usually drew like this axis. So assuming this is the x and this is the y, and okay, let's not make that y, let's make that z, and then this is our y. You'll see why it's a 3D sort of diagram soon. Each of these 3p orbitals lies on one of these lines. So there's a px that lies on the x-axis, there's a py that strictly lies on the y-axis, and then a pz that lies on the z-axis. So it looks like this jumbled mess, but essentially that's what this is, which is why we can have these different p orbitals interacting in the way that they're often seen to interact. So that's kind of the reason why they form these different molecular orbitals, like the sp orbital. So basically how this sp orbital forms is any one of the p orbitals, whether it's px, py, pz, would, sorry, yes, it would hybridize, but I will introduce that concept just a little bit later. But I want to say it fuses with an s orbital to form an sp molecular orbital, which is this sort of fish-like shape. You can associate these shapes with anything realistic. So this often looks like a fish to me, with two weird eyes. So I sort of associated with a blue whale, how a child would draw a blue whale. See, in fact, all we need to do over here is just add the fins, and we have our blue whale. Ta-da! But nope, we're not gonna do we're not gonna do that. The molecular sigma orbital I associated with a toffee that also has two eyes. All of them have two eyes basically, but this does look like a toffee. It looks so much like a toffee. So the CC, since we already know the head-on overlap of two p orbitals, these could be px or py, and they combine to form our molecular sigma orbital. Alright, so our next example is ethene. Ethene is essentially ethane with a double bond. So ethene has everything that ethane has, minus two hydrogens and adding a double bond. So the way we have to look at this is the pi bond and the sigma bond. Because we already know the bond between the CH, it'll be the exact same as described for ethane. That's the same for every CH bond in carbon molecules throughout. Or I should rather say organic molecules. So the CC, the sigma bond, is the same as described here. There's not much difference. Alright. And then the pi bond is basically what I drew above. So our two different pi orbitals, whether px, py, pz, they overlap sideways. The lobes overlap sideways, and then they form this weird, let's say, hovercraft-ish. It looks very futuristic, I can't lie. It looks like a cylinder that wasn't completed as a cylinder. Low key, all that's needed to be completed were these two vertical lines, and it would have looked exactly like a cylinder, but it doesn't. So you gotta combine these two molecular orbitals, I would say, to showcase how the bond looks like. So this in red is our sigma bond, which is here our toffee shape. And then on the top, I basically drew this structure, but sort of expanded it so that you can see how it actually looks like. So we have these two big oval-like lobes here. That's the electron density where we are most likely to find the electrons within that pi bond. Since it's sort of distributed evenly above and below the sigma bond, it's a sure shot that we're going to find two electrons here. Over here, it could be evenly distributed. So the electrons could either be here or here, since it's both above and below the plane of that sigma bond. So that's how you would describe it. I don't think I've ever encountered a question where you would be told to draw this. I've drawn this so that it's very easy to visualize. And indeed, it does look kind of simple to visualize. But that's basically how this works. And now we move on to hybridization. So hybridization is basically the mixing of atomic orbitals to form covalent bonds. Essentially the same thing as forming molecular orbitals. So what we're going to look at in hybridization is how these atomic orbitals come together to form a molecular orbital. Alright, so there's three different main hybridizations we will be looking at. I already introduced you guys to the sp orbital. So right now we're going to look at an sp3 orbital. An sp3 orbital, so you can tell the sp orbital was one s orbital and one p orbital, but an sp3 would be one s orbital and three of the p orbitals. So we have our px, py, pz. And 1 plus 3 will give us 4, right? So we get 4 of these sp3 orbitals. This is how the sp3 orbital looks like. It's a tetrahedral shape. And I will see if I can include an image of a tetrahedral molecule. But essentially what it is there's a molecule there's an atom which is pointing upwards, so it's up. If you have those chemical models, you can easily put it together and visualize, but most of us don't. So I'm just going to describe it and put a picture. So essentially one of the molecules is pointing up. So I'm going to assume that we're looking at this molecule face to face. So this hydrogen is above this carbon atom, right? This hydrogen is essentially like how do I say it? Okay, this hydrogen is to the left of the first hydrogen, the one that's on top, but it's in the same plane. So it's in your same line of vision. It's not like behind the carbon, it's not slightly above the carbon, it's in the same plane as the other hydrogen. That's why these two have these straight looking bonds. We draw a wedge for this hydrogen at the right because what we are trying to say is that this hydrogen is actually behind the carbon or behind our initial hydrogen that we started from. So I'm just going to label these hydrogens to make it easy. This is H1, H2, H3, H4. Sorry for the haphazard labeling. But basically what I'm trying to say is this H3 is behind the carbon. So it does not lie in the same, I want to say, line of sight that this H1 is. It's not in the same plane. As for this H4, it's ahead. So it's pointing out, it's projecting out of this paper. If this molecule was in front of me right now, let's say I lay it flat on a paper, then these two would be laying flat. This would try to escape behind the paper, and the fourth hydrogen would be projecting out of that paper. Uh, I wonder if that's a good enough explanation, but that's essentially what the shape is supposed to look like. Sort of like a pyramid base at the bottom here, like a triangular pyramid base, and then there's the top sticking out. So each sp3 hybrid orbital overlaps with an SH orbital to form sigma bonds. So we know the CH bond is an sp hybridized molecular orbital, and that's what the explanation is about. So these four sp3 orbitals combine with the four uh, sigma, sorry, combine with the four s orbitals of these hydrogens respectively, and that's for the sp3. Now we're moving on to sp2. So what sp2 is about, similar to sp3, but sp2 is one s orbital and two p orbitals. What this means is the third p orbital was not available for hybridization. That indicates that it was used in pi bonding. So what this means is an sp2 hybridization will be found in molecules with double bonds. And I say double bonds because sp is normally found in triple bonds. So we don't associate sp with double bonds. So we have one s orbital as usual and two p orbitals this time. They could be any one of the px, py, pz, and these combine to give us three sp2 orbitals. This looks like a fan. So this is a very planar molecule. I'll say planar because planar means flat. So if this was lying on my iPad or on this paper right now, none of the molecules will be going behind the paper or in front of the paper, which is why the bonds are having all of them have straight lines like this. Even the double bonds, because they're not moving behind the paper or in out of the paper. They're all in the same plane. So this is because one p orbital is occupied in pi bonding, so does not hybridize. So I explained that already. And the three sp2 orbitals, they form sigma bonds with the two individual s orbitals from these two hydrogens, and also the the p orbital from this carbon that's left. So this carbon, this molecule is sort of incomplete, I'm sorry, but if I complete this, basically it's a mirror image. So these two carbons both have three sp2 orbitals. So we say this molecule is sp2 hybridized. And later on I'll tell you a trick to determine how these organic molecules, you can determine their hybridization. We usually determine the hybridization of the central atom. So just to let you know. And then the sp. So sp is essentially one s orbital, one p orbital, any one of them, and they form two sp orbitals. These two sp orbitals combine with an s orbital from the hydrogen to form a sigma bond, and a p orbital from the carbon to form to form a sigma bond as well. Then we have the p orbitals that form pi bonds. So there's two pi bonds in this molecule. It's also incomplete. There's supposed to be a hydrogen here. So again, a mirror-like molecule. This is actually ethine. So yeah, that's it for hybridization. It's very simple. So now let me tell you the trick. The trick is that, so what you have is these, okay, so I'm going to use CH4 as an example. In CH4, you can see that there's 4 bonds. So there's 1, 2, 3, 4 bonds, right? When we're determining hybridization, there's this formula that I like to use. So to determine the hybridization, it's usually, if you want to know whether it's sp, sp2, sp3, you do sp n minus 1, where n represents the number of atoms your central atom is bonded to. Yeah, my bad. Okay, so the number of atoms our central atom, which is carbon, is bonded to in methane is 4 atoms, which is hydrogen 1, 2, 3, and 4. Hence, it would be sp 4 minus 1, which is sp3 hybridized. And that's how you determine the hybridization. And this works in double bonded molecules as well, because taking this carbon, which is our central atom, it's bonded to 1, 2, 3 different atoms. So it would be sp3 minus 1, which is sp2 hybridized. And that is true. So that's basically a formula to help you guys to determine which hybridization a molecule is, or its central atom belongs to. Usually hybridizations help with shapes of molecules to determine what shape the molecule would be. So like this hydrogen, methane is tetrahedral, so sp3 means the molecule is tetrahedral. That's how a lot of people like to learn it, but we'll soon determine that you can actually figure it out when you look at the molecule according to a certain theory. Okay, so the next thing, it's just a quick um, thing that the syllabus said must be talked about. So we have bond energy. Bond energy is defined as the energy required to break 1 mole of a particular covalent bond in the gaseous state. And gaseous state is very, very important, guys. Please do not forget that. I've gotten penalized 1 mark for forgetting that, and you will always, always need the 1 mark. Trust. So just memorize this definition. There's no other way around it. I'm sorry. But it kind of sticks as you go along. A lot of these things tend to be at your fingertips once you're actually actively preparing for those papers. So the next definition is bond length, which is the internuclear distance of 2 covalent atoms. Okay, that is self-explanatory. What I want to focus on is bond length is inversely proportional to bond energy. What this means is the lower the bond energy, the higher the bond length, or the longer the bond length of that molecule. So the reason why this makes a lot of sense is because, let's say if you have atom A and atom B, and the length is like really, really short. The bond length is, let's say, I'm going to use 1 nanometer, even though that's probably highly inaccurate. And then we have molecule A and molecule C. I'm going to say this is 2 nanometers. What this means is the electrons in this bond, that will be our electrons, and this looks very weird from a mass perspective. So these electrons are attracted to the nuclei of A and B much more than the electrons of A and C. Because if A and C have a longer bond length, it just means that their nucleus isn't able to come closer enough. So that just means it's not able to attract those electrons more. so that bond isn't really closing in. The more the attraction, the tighter that nuclei would be. So it makes it more difficult to break. So because it's more difficult to break, you need more energy, whether that's thermal energy, but it becomes more difficult to break the bond with the lower length or which is shorter. So that's kind of the reason. And when often you'll get bond data in questions and you'll be asked certain things such as which molecule would have a higher reactivity. Basically, the molecule that has a low bond energy has a very high reactivity because it doesn't take that much energy to break down that molecule. Hence, it reacts way better than a molecule that would take more energy to react, if that makes sense. And then you can associate that with the bond length of that molecule and go on further to explain that since a molecule requires less energy to be reactive, it means that its bond length must be really large. And essentially that makes sense because it's proven with data as well. Okay, so enough with the bond energy. We're coming to the last part of this video, which is shapes of molecules. We're going to be using VSEPR theory. I like to call it VSEPR even though it sounds really weird, because what is this? How do you I don't even know, and don't get me started on the weird chemistry names. But basically, VSEPR, we call it VSEPR. Valence shell electron pair repulsion theory. Very long, but what it means is, I'm going to use water as an example. What it means is, in a molecule, most likely a covalent molecule, you will have a lone pair of electrons, which means the electrons that are not involved in the bond directly. So this is the bonding pair of electrons, the pair of electrons that are directly involved in forming that covalent bond. The lone pair is not involved. Now, when we're determining shapes of molecules, it's important to note that pairs of electrons like to repel each other, because as you know, like charges cannot stay together. However, how much is this repulsion? Does it vary? It does. This is how it varies. Lone pairs repel each other more than they would repel with a bonding pair. So these two lone pairs over here, they don't like being close to each other at all. They also don't like being close with the bonding pair, but they prefer that over being close with each other. I'm gonna explain it like this. Think of it as hydrogen's circular electron is a friend of the the X electron of the oxygen. So these X electrons would rather get with the circular electron than get with themselves, since that's their preference. So they would want to distance themselves but get closer to those circles. However, they don't want to be too close to that circle because technically that's against the laws of physics. That's my weird explanation for that. And also the bonding pairs do not like getting close to each other. So it's basically like all like terms do not like being close to each other, and they like being close to the opposite ones. You can think of it as that. As we already know, like repels like and they attract the opposite. So these lone pairs will repel the lone pairs more, bonding pairs repel bonding pairs, but they don't do it with as much hatred as the lone pairs do it. These guys are certified haters. The bonding pairs are just learning how to hate on each other. That's how I will explain it. Because of this, water gets a bent shape. I say a bent shape because when I draw this molecule again, I will draw it like this. So this is how it would look, like a V. You can either call it a bent shape or a V shape. Examiners will mark both of those correct. And you absolutely need to draw the lone pairs. As you can see, the lone pairs would rather be closer to these bonding pairs of electrons. The bonding pairs are quite far away from each other. This angle that water is at is measured as the bond angle. The bond angle is between the two hydrogens. So it's not with the central atom. It's between the two hydrogens. The central atom is involved in other bond angles in other molecules, but we'll look at those ones. But for water, we usually measure the bond angle between the two hydrogens, and that is determined to be 104.5 degrees. That's how water is. And this gives water so many unique properties that I'll talk about in the next video. Okay, so I'm going to go to the examples. This is the last part of this video. So our first example is BF3, boron trifluoride. So boron trifluoride, we already drew this molecule earlier in covalent bonding, and boron is electron deficient, as I had explained back in that video. Boron forms 3 bonds with 3 fluorine atoms, and these 3 bonds, now this is similar to an sp2 situation. So an sp2 hybridized molecule such as this one would have 120 degrees bond angle between the 2 fluorine atoms. So, sorry, not between the 2, between any 2 of the fluorine atoms. And we recognize this shape as being trigonal planar. Trigonal because it obviously resembles a triangle, and it's plane, so it's like flat. Basically, if you put this molecule on a piece of paper, it's flat, and that's the bond angle. So that's just kind of like the angle between, let's say, the corners of a triangle, but they're focused on that center point. So like this is the triangle, and so the angle between these 2 corners here, that would be the 120. Alright, and what we have here, CO2. CO2, now we already know that what oxygen has these 2 lone pairs of electrons. Both of these oxygen atoms have them, so that effect is overall cancelled because it's a very symmetrical molecule. Symmetrical molecules are usually planar. That's a sort of trick that you can remember, such as ethene. It's symmetrical and it's planar. So the bond angle between the oxygen and the carbon, or even the oxygen and oxygen, would be 180 because it's very straight. It's a straight molecule. So we refer to the shape as linear. So linear molecules have 180 degrees bond angle. And we already discussed tetrahedral shape in detail, so I won't spend much time on it. I will say that the bond angle between these 2 hydrogens is 109.5. There's no lone pair repulsion here. It's strictly bond pair repulsion. So that's why the figure is like this. You just have to remember the bond angles. based on the shape, and you can remember the shapes based on the hybridization. So they're all interlinked, and very often this stuff remains in your head. You can often write this down, like probably try to remember these every day. It's very simple because there's limited examples in the syllabus. You won't really get asked that often on different atoms. You would get these similar or much more easy examples in practice. Okay, now the difference between, you see how this molecule, oh, I forgot one thing to mention, guys. In the SP, in the hybridization rule, this rule, the N is not just the number of atoms, blah blah blah. It's also, you have to add this. I am so sorry for this. You gotta add this to the lone pairs, number of lone pairs. The reason I say this is because ammonia is also sp3 hybridized. Yeah, the only difference is that it does not bond to four hydrogens like carbon does. But it's also sp3 hybridized in this molecule, similarly to the carbon here. Now, why it forms a different bond angle is because of the lone pair. And we know that lone pair, bond pair, that repulsion is stronger than the bond pair. So this lone pair sort of pushes those hydrogens together, and that reduces their bond angle. I'm sorry for this. This bond angle is supposed to be between these two hydrogens. So that's 107 degrees. Lesser than the 109.5 because the lone pair pushes those hydrogens together due to the repulsion being strong. So its shape is pyramidal because when you do a base, well, if you put this molecule on a paper, it would resemble a pyramid because of the way it has a triangular base. So it's pyramidal. Okay, now come the octahedral shape. Octahedral, well, I would say it's octahedral because of the weird, I think it has probably 8 angles-ish. But basically, it has a 90-degree angle between any two fluorine atoms. So these two fluorine atoms in SF6 are behind the plane and in front of the plane. All these four are within the same plane. If these two weren't there, I would refer to this as a square planar um, molecule. But basically, this is how SF6 looks like. And that's the bond angle. It's 90 on the dot. Alright, we have trigonal bipyramidal. I know these shapes are very weird, but trigonal bipyramidal is a combination of trigonal planar because of this 3F situation that's the same as BF3, and that gives you the 120. Bipyramidal, the reason we call it bipyramidal is because if you remove any one of the, I would say, back and front fluorines, then this can act as a pyramid when you put it on a sort of piece of paper or any flat area. This would become a pyramid, and it would become a pyramid in both ways, front or back, which is why you call it bipyramidal. And that angle between the okay, so we can call them, I forgot what they call them, but I feel like they're called equatorial and another one. I'm so sorry for this. So this is I'm gonna call it longitudinal and latitudinal. Uh, or you know what? I'll call it vertical and horizontal. So this vertical fluorine and horizontal one, they form a 90-degree angle, but a vertical fluorine with another vertical fluorine form a 120-degree angle. So with trigonal bipyramidal, that's what they form. Alright, and then we have, oh yeah, this is another example of a planar molecule. Like I said, sp2 hybridized. The central atom is sp2 hybridized. So we already know it forms a trigonal planar shape. So that gives you the 120-degree bond angle. And I would like to show you the difference. So this pyramidal shape can become a tetrahedral shape once it bonds to another hydrogen, as I demonstrated in dative bonding. The ammonia base becomes an ammonium ion once it sort of gets that proton, and it'll give you that bond angle that's present in methane. Okay, so that's all for this video. I feel like it's too long already, but thank you guys for listening. I, as stated at the beginning, I will put timestamps in this video. If you have any further questions, please do not hesitate to reach out in the comments. I will address comments. And thank you guys. Subscribe the subscribe to the channel, please. Bye.